Okay, I should have the camera fully restarted. Any, that's good to hear. Thank you, Caitlin. Kind of a strange error. I don't know what would have caused that, but leave it to be just nearly the last week for strange technical glitch. Well, welcome back, everyone. Let me open up a new page real fast here. These screenshots go away after unsharing the screen, or the annotation, I mean. So we'll just use the screenshot here to visualize it. And again, sorry for the technical glitch. I'm not too sure what could have caused that, but we always could try the technical thing of just unplugging it and plugging it back in. So that worked out this time at least. Amy asked an important question at the very top of the chat about information that's going to be on the final exam, which is the right time to start asking those kind of questions. As far as the final exam goes, it's going to be fully comprehensive. I'm not going to give extra weight on any one section whatsoever. Even on chapter 8, there's 4 sections all the way up to unit 8D that have not been on any exam. But as far as chapter 3 goes, there's going to be anywhere between 2 or 3 questions that I'm going to ask. I don't want to overload the final exam with a whole bunch of unit or chapter 8 questions altogether. So a great way to think about what could be on the exam is just put your exams 1, 2, and 3 together. I'll have this fully graded, hopefully on Friday, Saturday morning at the very latest. And then that's going to be a really good set of sample final exam questions, just your exams put together. And then I'm going to be showing some review problems encapsulating what's going to be on the final exam for chapter 8 as well. Unit 8D is going to be the final unit on the exam. But again, there won't be any extra weight on any particular chapter, not including chapter 8. But other questions at the moment to start us out so far? Awesome, glad to hear that. And maybe one more comment along the lines is a great way to make yet a new version of the sample final exam would be not just put exams 1, 2, and 3 together, but also if you go through quizzes 1 through 13, just as one big packet, quiz 1 through 13 is a pretty decent all-encompassing sample final exam as well. The final exam is probably going to be a little bit longer, more like along the lines of about 15 questions. So this quiz 1 through 13 comes shy a couple questions, but that will give you a great hint on what is possible for the final exam as well. Moreover, once we get across the weekend from the current week and start going into week 15, after I get fully caught up on grading, my next goal is to start posting all the information that's going to be here, just like we did on the other exams. I'll have a short formula sheet, just like we've had for exams 1, 2, and 3. And then I'll post 2 versions of sample final exam problems. Yes, that's right, Amy. The real final exam is going to be a 2-hour exam. And a lot of people interpret that in a lot of different ways. Some people write an exam where you're going to be writing for 2 hours and your hand is going to be probably really tired and sore at the end. But for me, what I'm going to try to do is for this well-prepared average student, if you've gone through all the review materials, you're fully caught up with the course, all the quizzes, and so on. If you're well prepared for the final exam, I'm trying to write an exam that's going to take a length of about an hour to an hour and 20 minutes. So that about 40 minutes remaining time is really just for you to double check your work, not feel like you're going to be rushed on this exam. So you'll be given 2 hours of exam time, but I'm not trying to write an exam that's going to go for a full 120 minutes. So there'll be extra time, not as much stress as it kind of seems as a 2-hour exam. Other questions at the moment? Yeah, as far as testing center scheduling goes, definitely schedule it for the 2 hours. But I'd say absolutely use all that time. But again, the 2 hours has built-in time just for checking your work. Well, again, we're going to talk a lot more about the final exam. Essentially, we have an ordinary week that we're getting through after getting through exam 3. We're going to have our typical lecture that we're getting through on Wednesday today and Thursday tomorrow. Next week, when we come back on the 27th, As far as the schedule goes in the syllabus, it says we're going to have another lecture, but really all we're going to do on the 27th is just finish out whichever topic we were working on. So probably we'll be in Unit 8D. We'll just be finishing off the work there and then immediately converting into reviewing for the final exam. And we'll take the full day on both Wednesday and Thursday for reviewing for the final exam as well. I'll post the same kind of materials like we saw down below here, and we will go on a review based on that. Well, again, we'll talk a lot more about the sample final exam, or excuse me, about the final exam as we get closer and closer and post the sample final exam materials. But other questions so far? Okay, well, for what we're doing today, we're going to finish off the Unit 8C on the so-called real population growth. Also, we have our quiz number 12 that's going to be due on Thursday. And the other nice, exciting things about our schedule is this is going to be the last official unit for our course. We took a little bit extra time in Chapter 5 for the pacing, and so we didn't get into Chapter 12, but that's okay. This is going to be a great last unit to round out the course. And that means quiz number 13 is the final quiz for the entire semester. Yes, absolutely, Caitlin. I intended to work on starting grading exam 3 on Friday. And I should be able to complete the grading on Friday, so you'll be able to check your Canvas results here under exam 3. I'll send back the feedback on the questions and so on, just like for exams 1, 2, and 3. If it ends up taking a little bit extra time, if grading just goes a little bit slower, I'll have it done sometime on Saturday morning at the very, very latest is my goal. And again, as soon as the exams are completely graded, I'll be turning into posting information here as far as the review materials goes for the final exam. Oh, another thing I forgot to mention is there's going to be extra credit opportunities. I'll have 2 total. This is just the first extra credit opportunity. Really, I guess there's kind of 3 in a certain way. One extra credit opportunity, I'm not sure if we've discussed this yet, so we should at some point, is going to be related to your final exam grade. So the idea is, let's just imagine a fictitious student, and this student got a grade of maybe on these 3 exams. Suppose the grades came out maybe kind of low on exam 1, getting used to the course, 70.3. And let's make it be a kind of a comeback story. Let's say on exam 2, this person got 79.3. On exam 3, it was a 84.6. Then the way this extra credit opportunity is going to work is if the final exam score comes out as, let's say it's 85.4. This says if your final exam grade is higher than your minimum grade among exams 1, 2, and 3, the final exam grade will do a full swap, replace the minimum grade specifically, as say at 85.4 in this fictitious example. So there's an opportunity to make a strong comeback. If you had a weak exam amongst any one of these 3, then I feel like that shouldn't be something that really sticks to your grade, just having one off day on one bad exam. If you make it up by coming back strong on the final exam, I'll consider that a way to wipe out the minimum grade. Does that make sense there for the extra credit opportunity? Okay, and I want to emphasize this extra credit opportunity cannot harm your grade. So if maybe the final exam grade came out as a 70.1, then all 4 grades you would see there would just stick. The extra credit opportunity wouldn't take place. I'll be posting another extra credit opportunity as far as a course evaluation goes, but as far as I understand, the course evaluations are not yet open, so I can't post it yet. It says up here, the course evaluation starts on the 27th, which is going to be on Monday. So I'll be posting another extra credit opportunity relative to completing the course evaluation. This one has a due date. It closes on the 10th. And as far as I understand, the math department does not have any control over that whatsoever. So if you don't get the course evaluation done by the 10th, then that's when that particular extra credit opportunity would close. And the final extra credit opportunity is not exactly an extra credit opportunity, but it's really an opportunity. As far as your grade goes, if there's any work that went past due in my lab, or maybe any section where maybe you didn't get to all of the problems or some of the problems you didn't get to fully 100%, in my lab, you can always go back and fully complete any section and get it back to 100%. So in a certain sense, that's a type of extra credit. It's really the main credit of the course. And same applies as for quizzes. If any quizzes were past due, if any quizzes were late, then you can still do them for full credit. At the end of the semester, there's a statement in the syllabus that says, if you had a couple quizzes that were low, when I compute the final grades for the class, I am dropping the lowest 2 quiz grade scores. And we'll talk a little bit more about these things again when we come back on our review week, but those are the announcements so far. Any questions or other further comments to start us out? Okay, well, let's go back to our unit 8C, real population growth. Again, it has a weird title when it says real population growth because we were doing some honest population growth in unit 8B. One theme when it says real population growth is looking into net growth rates in terms of birth rates and death rates. So the birth rate versus mortality. And this can go down an even bigger rabbit hole if we take into account effects on, say, immigration, people leaving the country or migrating to the country. The recap problem here that we did was for specifically the United States. We looked at birth rates across these 3 different selected years, saw that it was falling. We saw that the death rate, it fell by a small amount in 1995, but then increased by a slightly more significant amount in 2019. That using the net growth rate, taking both pieces of these information together, we find that the net growth rate per 1,000 people was a 6.8, dropped to a 6.5 in 1995, and then started to, I think we use the word plummeting, collapse in a certain sense, started dropping really fast in relative terms in 2019. Based on that, we had to make a prediction on how the country's population will change in the next 20 years. And all we said was, since the net growth rate is plummeting, we predict the growth will be negative in the next 20 years. And so the population will decrease in the next 20 years. So that was our write-up for this problem. And we had to be really honest when we did this problem that the population of the USA is probably not going down in the next 20 years because we're not taking into account migration whatsoever. So only looking into these 2 variables, birth rate minus death rate, that's our prediction. We're about to do it again for another country, Afghanistan. But any questions at the moment with this recap problem here? Okay, so here's the problem that we left off then last Thursday. Looks like we did all the major computation work. We applied the same formula. I just copied and pasted it down to this spot in the notes for easy reference. But now that we're looking into an Afghanistan, same unit, same years, but very, very different values for birth rate and death rate as well. Their death rate started off very, very high, but now it was below the levels in 2019 of even USA. Birth rate was surging in these years, but it's still quite high here, but it's starting to drop down. And so when we looked at taking both things into account, there's some very different values comparing birth rate and death rate. It's pretty stable in a certain sense. The USA, these values are smaller, but it really collapsed in the last year. Here it's more of a increasing to a peak and then coming back down closer to the 1980 values. So if we were to make a prediction based on these trends, in my lab, it's definitely an easier question because it's really just multiple choice. So it kind of guides you into the answer. For this, it's kind of a more of an open-ended question. So if this was, say, an exam question, anything that you say that's correct based on the information we see here can't really be marked down. So say anything that makes sense, and then you're in great shape. Well, if the net growth rate is always a pretty large figure, and it doesn't seem to be collapsing like in the last problem. Sure, it went down by 6 per thousand people, but in relative terms, in percent terms, it didn't go down by as much as what we saw for USA. So we might say something along these lines. In the next 20 years, the net growth rate, we don't know where it's going to go, but if a downward trend based off just these two selected years continues, we can say the net growth rate may continue to fall. So let's say that here, the net growth rate may continue to fall, but will likely still be positive. We just don't know what specific value. For the USA, we were worried that it would go negative because it dropped to 2 per thousand people. So it's easy to imagine that in the next 20 years, it might be, say, -1 per thousand people. But here, if we believe that it still may be positive, again, we are making a prediction, so it's a very subjective response. This means the population will continue to grow. So that's our prediction for how the population will change. We're probably expecting growth, probably pretty decent growth for Afghanistan as well. Well, again, there's a lot of takes on this one. Anyone have a different take or any questions or comments with this? Okay, well, that's kind of concludes the middle topic in this Unit 8C. The first topics we were looking at were really just a complete refresher on these problems that we did in the prior unit. So this one really kind of dips into Unit 8C quite a bit using these formulas, specifically the one for growth rather than decay. For the next problems we're going to take a look into is we're going to look into a new growth model called logistic growth. And I felt when I read this section in the book, I'm reading these sections for the very first time along with you. When I read this section, it was kind of strange because what I was expecting was the model that would tell us the new value based off of the initial value. Those formulas are absolutely out there. They're easy to Google and come up with. I actually wrote it down just in case people are curious. But as far as what Unit 8C is focusing on specifically, we're just focusing on the logistic growth rate itself, just that quantity alone. So let's work through this brand new definition here just to see what it's all about, and then work through the next couple examples dealing with these kind of formulas. So first definition is all about the carrying capacity. Any particular species on the planet, whether they're humans or otherwise, there's an interesting discussion on what is the carrying capacity for that organism. The carrying capacity is defined to be the maximum sustainable population size. That is, the largest population the environment can support for extended periods of time. A population can exceed its population size that's larger than the carrying capacity, but it may not be stable any longer. That population is going to likely collapse if it goes beyond a true carrying capacity. So our author talks a lot along the lines of what is the carrying capacity for the human race, for example. In example 5, we're going to talk about elephants, a little bit more toned down kind of a context. But we'll go and look into carrying capacity as it relates to humans in the next examples. So that's our first big definition with this. And even if we're thinking about something simple, say bacteria growing in a dish, a petri dish of nutrients, that has a carrying capacity too. The bacteria may in fact grow through this exponential model that we have here in the prior unit, but eventually, after enough time goes by, this growth rate is going to fail. The population model here is going to collapse. There's just going to be a lack of space, a lack of nutrients for that bacteria, and that applies to any organism whatsoever. These exponential models work in the short time, but not for the extended periods of time. So if the exponential model fails, we need a new model, and that's the logistic growth model. This definition only gives us the logistic growth rate, not the full model to say what a forecasted value might be. Again, if you're curious about that, it's easy to look up and just let me know. I could post it on the notes. But this is what all the homework exercises are going to be about. Coming up with a new growth rate that's realistic in long periods of time. So here's how the definition goes. It says, when a population is small relative to the carrying capacity, the logistic growth is actually true exponential, very close to an exponential growth model. With fractional growth rate, when it refers to that, it's talking about the P that we would put here, the growth rate, usually as a percentage. With fractional growth rate, close to the base growth rate, R. So our author is kind of sneaky when he throws in that statement there. And this is what's making the definition tough. We're tracking carrying capacity. A so-called base growth rate R is another quantity we have to track. And it goes down right here in the logistic growth model. So the base growth rate R is the fractional growth rate that we expect for true exponential growth when a population is small. But the population starts growing bigger and bigger and bigger. It gets closer and closer to the carrying capacity. And when that happens, the base growth rate no longer is the true growth rate of that population. It becomes the logistic growth rate. It says here, as the population approaches the carrying capacity, the logistic growth rate, the real rate of increase, gets closer and closer to zero. In other words, as this population here gets larger and larger, reaches a carrying capacity, this gets closer and closer to 1 minus 1. So the whole thing approaches a zero, meaning it's not growing any further. The population growth rate is going to become nil, zero at that point. The next part says the fractional logistic growth rate at any particular time depends on the population at that time. And that's this part right here, the population size. It also depends on the carrying capacity and the growth rate R. So we throw in the population size at any given time, the carrying capacity as well, and this gives us the logistic growth rate. Then
I have a question real quick. Can you explain the base growth rate again? I don't exactly understand what that is.
Yeah, absolutely. As far as the base growth rate goes, another way to consider it is, let's put in just a really fast kind of like a calculator example. So for a fictitious population, let's suppose R is maybe a 0.025 for a 2.5% growth rate. Multiplied by 1 minus, let's suppose it has a carrying capacity of maybe 100,000, whatever that species is. And let's say the population size is currently 100,000, just to see what happens. It tells us then the logistic growth rate is zero. It's not growing. The population has reached its carrying capacity. But now to answer your question, what is R, the base growth rate? Let's see what happens as the population size, the thing in the numerator, gets smaller and smaller. Let's say it's just 1,000, or I guess 100. Let's say it's 100. Now maybe 1,000. If it's 1,000, notice we're at 0.025 here, and at 0.02475 here, the numbers are really close. Drop to 100, and this number down below, the logistic growth rate, it actually rounds now to that 0.025. there's 10 members of the population, we get this. That's even closer. One member of the population, this becomes nonsensical because the population can't grow now if there's just one member, right? It's kind of stuck at this point. But that's really close to 0.2499 or 0.25 altogether. Put in exactly zero and the population's wiped out. But at that case, the population's base growth rate is 0.025. So what this numerical experiment is saying is the base growth rate R is the maximum rate at which the population can grow. It's a maximum in the sense that it's really the upper bound. The population can't quite grow at that rate. It can get very, very close to it when the population size is very, very tiny. And as the population gets bigger and bigger, this entire logistic growth rate will just be smaller and smaller than R altogether. Does that make sense so far with what's going on with the base growth rate?
I think so. I understand that a little bit better.
Awesome. Glad to hear that. So going through this whole, again, it's a big paragraph of a definition again. It says when the population size is small relative to the carried capacity, logistic growth is exponential, and the growth rate is essentially the base growth rate R itself. Echo says, so is base growth rate just the percentage rate the population grows in a given time frame? Almost. If we assume that the population is growing exponentially, always, then that would be true. But the moment we say we're going to assume the population actually grows to the logistic growth model, we want to think of the base growth rate as the fastest the population could ever possibly grow as, the maximum growth rate possibly attainable. Well, other questions or comments at the moment? Again, it's kind of a beast of a definition, right? When you think about this, let me highlight this temporarily. Let me throw in a quick calculator, as well as this formula down here, where we're focusing on the doubling time. So what this shaded line is saying now, altogether, with the base growth rate R, is that the population size is small. Let's say it's back to 25 individuals in this population. When the population is small relative to the carried capacity, logistic growth is actually well modeled by the exponential growth model, this one down below, where we take the initial value, 25, multiply it by 2 to the power of t divided by t double. P right here would just be the 0.025, or rather, it would be the 2.5. We'd have to unconvert it from a percentage. But then it says that as the population approaches the carried capacity, as it gets larger and larger, this growth rate is just not sustainable anymore. The exponential model fails. So if we get, say, around 90,000 individuals, it's dropped way, way down. So this is the true growth rate. And the base growth rate, it was for an exponential model, but in a very short time, and also only for very, very small population sizes relative to a carrying capacity. So again, this is tying together a whole bunch of ideas all at once. And this is finally what the author is really trying to say when he says this is real population growth. Usually decent population growth models are actually logistic models. Exponential models only working in the short term. Other questions so far with the definition?
No, but I have a question. So when they give us the base growth rate, it'll be like in a percentage, and then we always take that and convert it into a decimal for R.
Yeah, absolutely. Thanks for mentioning that. That was another thing that's really tricky where this was the one-off, the one time where we don't actually convert to a decimal, we just drop the percent symbol. But R, in this case, like on pretty much every other formula in the course, we should say here, just for emphasis, R must be converted to a decimal. So divide whatever it is by 100. So whatever they tell you the base growth rate is, divide it by 100, plug it here, and now we're working with the formula in the correct way. Again, thanks for mentioning that. That's an important fine point about all the formulas in Unit 8 so far. Other questions or comments so far? Okay, well, another thing that's tricky about this whole problem is not really the author's fault here, but the way the problems are written when they get converted into MyLab are tricky as well. That says find the actual fractional growth rate, where actual is kind of a weird word to emphasize. When you see that kind of emphasis, what this is telling us to do is find the logistic growth rate. So I wrote my questions here to be pretty similar to the way they're written in MyLab. But if this was converted into an exam question, I would probably say, just to be specific, find the logistic growth rate so we know we're being keyed in to use this formula up above here. Okay, so we got through the definition. Next is the context for the brand new problem that we're going to take a look into.
Question real quick. So when it says fractional growth, that is actually logistic growth.
Exactly. They're referring to, when they say this entire thing here. Absolutely. And, now that you mention that, that was one of the things that was pretty weird about all of the questions that they posed. Let me see if I can find another one just like that. Hang on. I know there's some other question that goes along those lines. I guess this is along similar lines. This one was asking for the fraction of the original tracer, or the fractional decay rate. Came up in several contexts. But yeah, that's some really weird wording as well when they say fractional growth rate, anything along those lines. They're still referring to the logistic growth rate. I guess one way you can kind of make heads or tails of that is when you come up with this rate, it's something along the lines of, maybe it's going to be for one particular problem, 0.013, but then you could just say that that's really 13 individuals per 1,000. So any growth or decay rate could be re-expressed in a fraction in that way, but it makes for an awkward question being written in MyLab. I wish there was a way for me to control or tweak those questions to edit them, but they're firmly set in stone coming out of the textbook. Other questions so far? Okay, well, with this close analysis on the moving parts of this brand new definition, we're going to put it into practice on this example 5. It says, deep within the dense tropical rainforests of Gabon, specifically within the protected confines of this real place, the Loango National Park, resides the African forest elephant. And these are smaller elephants, we're being told, but they're still gigantic. And they play a vital role as gardeners of the forest by dispersing seeds, creating clearings. More context tells us that Gabon's a pretty special place. It contains over 50% of the world's remaining forest elephant population, specifically that species there. So conservationists closely monitor their numbers. So far, this has been all just context. We're told, while the park provides a rich habitat, the population is ultimately limited by the availability of fruit trees and the physical space within the protected boundaries. We're starting to key in that there's a carrying capacity here, and we want to talk about the growth rates as realistically as possible using the logistic growth model. In a specific recovery zone of the park, ecologists have estimated the environment can sustainably support a maximum 1,200 elephants. But once they say that, sustainably support 1,200 elephants, they're talking about the carrying capacity. Words like sustainably, support, a maximum for a population size are all good kind of big buzzwords to say we're just talking about the carrying capacity itself. So as we're working through part A, we can start by saying carrying capacity equals 1,200 elephants. So that's one key item down. Next line says, consider a recovering population of forest elephants in this national park that begins growing exponentially at a base rate of 2.5% per year, but then follows a logistic growth pattern. So population size is going to be relevant somewhere along these lines. Oh, it looks like it's in part A. But when they gave us a base growth rate, this quantity right here, the wording has to say base rate to tie in directly with this base growth rate in the logistic model. We now have that R equals, it has to be converted to a decimal. So take this, divide by 100, it's 0.025. So that's all the moving parts so far from the context of the problem. And part A now says, find the actual fractional growth rate. What they mean is we're using the logistic growth pattern and we're trying to find the logistic growth rate. Again, I wish they would just say that. I'll be sure to just say it more bluntly in a real exam question if this one ever comes up in the final exam. Find the actual fractional growth rate when the population is 300 elephants. So we have a population size at 300. So using all three pieces of those information, we can now calculate the logistic growth rate for this particular elephant in this region that had the specific carrying capacity. One thought you might have when you're doing this kind of problem is it might feel kind of similar in all honesty. Even though we haven't done this problem very specifically, we've done stuff just like this. We were in chapter 4 looking into the power of compounding, and we're doing problems like, say, this one right here. It's the same kind of deal. We had to very carefully analyze the context, consider what the main formula is, what all the moving parts are, identify P, ARP, and the time amount, so we can just throw everything together. Same kind of skill of tear apart the context, find all the moving parts, so we can use the above formula right here is in play. We're doing the same sort of thing at its heart, just different formulas, different kind of quantities. Still, we have a rate. We still have not a principal, but a population size, and a carrying capacity is the very, very new thing. Now we're just going to plug it all into this formula that we see up above. So the actual fractional growth rate, again, we're going to call that logistic growth rate to be specific. Logistic growth rate is going to be equal to, we take R as a decimal, 0.025, multiply it against 1 minus, throw in population size, 300, divide by the carrying capacity of 1,200. These had units of both elephants and elephants, but we typically just drop them right away since they will cancel and write it in that format. So what this is telling us is if the population is 25% of the carrying capacity, then the real growth rate, logistic growth rate, isn't going to be 2.5% any longer. It should be smaller because the population size is getting closer and closer in each part of the problems to the carrying capacity. So if we throw this into a calculator, this is now 0.025. You can simplify this as a fraction if you like, but no harm in just dumping it all into the calculator just as it stands. We want to convert this to a percent. This part in red is instructions I forgot to put down after checking MyLab. So multiply by 100 to convert it into a percentage. And this is what we get. Actually, just to show the steps using the formula, let me leave it like this and then do the conversion in the next step, just so we can see the step-by-step process. Formula first, then conversion next. So 0.01875. Now as a percentage, let's hit it by times 100. And we were rounding this to 2 decimal places, so 1.88%. So if the base growth rate, the highest value it could ever have for growing for these elephants was 2.5%, then once it reaches a population of 300, the new true growth rate by the logistic model is 1.88% altogether. So in this case, this is more realistic for modeling the population. It's a critical problem for conservationists, so they can't use the exponential growth model in very long terms. Eventually, the population size of these elephants is just going to shoot right past 1,200, but then they'll see what happens in reality is that never happens. If they do exceed 1,200, the population's probably going to collapse. It'll have exhausted all of the potential food in its environment, for example. But this is more in line with what will really happen. This gives us a better forecast. Any last questions at all, folks, on the part A? Okay, good news about this kind of question, same as the one you'll see in MyLab, is if you can get it down once, the rest of them are pretty much the same kind of thing, just a different scenario. This one is asking us to do the same, but now the population has been revised to 600 elephants. So let's just assume maybe some time has gone by. We now want to know, once it's reached this size, the new logistic growth rate. The key thing about this formula, what makes it realistic, is that rate changes at every single change in the population. Even by 1 elephant, it's going to change. We always use the same base rate, the maximum exponential growth rate it could ever have for very, very small population sizes, 0.025. We're assuming the carrying capacity hasn't changed, or else they should have told us in part B. So we divide still by 1,200. The only thing that's changed is the population size is now 600. So now we're wondering what happens if we have doubled the size of the population. Again, this whole thing simplifies. This is really 1 minus 0.5. So we're taking 0.025 times 0.5, which is a pretty fast way to put it in the calculator. But in a lot of calculators, if you recall the last thing you calculated, you are just changing this to a 600. That's something you can do, say, like on the TI-30X2S. The up arrow can give you the last computation. That gives us, this is a value, 0.0125. We are then converting it to a percentage, so times 100. And it's same number, but different unit, 1.25%. So when it's halfway to its carrying capacity at 2.5%, it becomes literally half. In a certain sense, that makes sense, right? If this is the fastest it could ever grow at essentially the most minimal population possible, if we're halfway to the largest size of elephants that could be supported, the growth rate should be cut in half as well. And that's what this model is trying to reflect when we see these numbers. We'll try it again when the population is now at a very large amount, very nearly at the carrying capacity, 1,100. But any questions or comments at the moment? Okay, well, next thing to put down, if we are updating the population size to 1,100 elephants, we can now say logistic growth rate will now be equal to 0.025, following the formula down below or above with different values, 1 minus 1,200 again in the denominator, but now 1,100 in the numerator. New value, we're expecting to be quite small now because we're almost at the very end of the carrying capacity. Once we hit 1,200 exactly, the logistic growth rate goes to 0%. So the model kind of fails in that certain sense. Well, it doesn't necessarily fail. It's going to say the population is stable once it hits 1,200 and no change is going to occur. So if it reaches 1,100, we now have, oh, let me take that off just to walk through it in stages. We now have this number, 0.00208. Then hit times 100 to convert it to a percentage. To 2 decimal places, that's a 0.21%. And that's what the growth rate would be for these elephants. Assuming that they measured that number very accurately, the carrying capacity, that's what we're expecting the growth rate to come out as. Well, any questions at all, folks, with logistic growth rates at the moment? Okay, like we said before, if the population size reaches 1,200, we have a growth rate of 0, which says we're predicting the population to be stable. Will it really be stable? Probably not. It's just a model. It's not going to say with 100% accuracy and clarity what's going to happen to the population size of these elephants. But that's what the population's predicting. No change year after year. It's going to be 1,200 elephants. Although the book didn't explore this, sometimes what does happen with populations is they can overshoot their carrying capacity. So let's suppose something happened and for some reason there is 1,800 elephants and carrying capacity of 1,200. This would tell us that the growth rate is now negative. It's decreasing in its growth. The population is now collapsing at that particular logistic rate. So this can take for an account positive and negative rates all at once. But what we're exploring here is really just purely growth. So these will be the more typical numbers we see. So that's the logistic growth model in a nutshell. This is one of the main questions that we're going to compute with. And we have one more follow-up question that we're going to do to close out the notes. This one based off of human populations next. But any last questions or thoughts at all, folks, using this logistic growth rate model? Okay, for the next examples, we're going to Australia, but it's also a review problem, so we're also going to unit 8B. Again, I feel like 8C is kind of weird. It dips into unit 8B a lot. It's represented in the problems that were available to assign in my lab. But you know, if we are doing a review problem, that's okay in a certain sense. There's no harm done. So this one is going back to our methods that we did in the prior unit. So this doubling time formula is back on the table for us. And here's what we're trying to do. There was a 2020 census for Australia, and they found that the population of the island or continent is 26 million. I think currently it's closer to 27 million, but we'll use that figure for the 2020 census. Starting from this value, use the current annual growth rate of Australia of 1.4%, which includes immigration as well as births and deaths, so it's a pretty accurate growth rate, to estimate the population of Australia in 2048 and 2049. But the key part of this problem says, use the approximate doubling time formula. So we're going back to exponential growth models. We're going to use approximation formulas like before. But then that example 7 tries to bring it back to reality. The numbers we're going to get here may not be fully realistic, especially in the year 2099. It says, assume the carrying capacity of Australia is 60 million. An extremely debatable figure. And any carrying capacity for humans is very debatable. This one is a high estimate. Australia is a strange place where the population is mostly in the coastal regions. The interior of the continent is extremely hostile, dry, and unfriendly to humans. And so this is considered to be a pretty conservatively high estimate for carrying capacity. So we're going to look into what the growth rates really should be for logistic growth in the year 2020 after doing part A. The thing that's concerning about this problem is the base growth rate is missing. So we have to make an adjustment to this formula below. But once again, examples 6 and 7, you'll see the same kind of thing in the homework exercises for these examples, kind of relate to each other. So we'll solve this as a review problem and then do the more realistic problem down below in example 7. Well, any questions at all, folks, before we begin? Okay, well, to get the predicted population in 2048, let's cite the formulas we needed from the prior unit. First thing we want is T double. Using the rule of 70, we take 70, divide by the growth rate P. So we're citing this formula here, 70 divided by P. In this problem, when we were told that the annual growth rate is 1.4%, in this one and only one formula, we write P as 1.4, dropping the percent symbol, but doing nothing with the decimal. This is the one and only time we'll ever do this in this course. So that becomes 70 divided by 1.4. At this stage, we need the calculator. So 70 over 1.4 results in 50 years. Nice even number there. So if we assume the population of Australia keeps that annual growth rate and that it's growing exponentially, again, we're assuming that's an accurate approximation as well, population should double every 50 years. We want to compute population size in 2048, so we take the time, 2048. We have a population size, an initial value of 26 million, based on a 2020 census. So we take the difference, 2048 minus 2020, to get 28 years. Now, once we have that, we get to use this formula here. The new value, population size in 2028, will be the initial value, which is the 26 million by the 2020 census, times 2 to the power of t over the t double we computed. So putting this on paper, it doesn't hurt to just put it down as a reference. Let's screenshot it in. So there's our reference formula. We're going to say, I feel like we need a border now. There we go. The new value, or the population size, will be the initial value, which is 26 million, times 2 to the power of the time, 28, divided by the doubling time, 50. These both have units of years. Forgot to write that on that t variable there. So they often cancel. We just put it in that format. So then this becomes 26 million. We'll write in as just a 26 times 2 to the power, 28 over 50. And we're rounding this to the nearest tenth of a million. So we'll just say 38.3 after rounding. Million people. So that's our predicted population size in year 2048. Let me just park that formula there. Again, we've done a good number of these, so this is really just another review. It goes together with the next example, so no harm in doing it. And if we were to do it again, predict population size in the year 2099, all we need to calculate is the time. Take 2099 minus the base year 2020. We now have 79 years altogether that we're computing on. And then just redo the whole process with the 79 right where the 28 is. So we get to say population size is 26 million times 2 to the power, now 79 divided by 50. So if 79 years have gone by since the 2020 census, and bigger assumption, nothing's changed about the growth rate is also what we're assuming here. This is our forecasted population. 26 times 2 to the power, 79 over 50. So to the nearest tenth of a million, we're looking at 77.7 million people in Australia. In the year 2099. I don't know why we did go to the year 2100, but that's what the problem asked for specifically. Well, any questions at all, folks? Getting through those two review problems there? Okay, major reason for doing the example 6 is once again to see how it compares with looking into methods in example 7 next. And notice already that number 77.7 million is kind of skeptical. Exponential growth models over 79 years, probably not very accurate at all, really. And the 77.7 million people has exceeded an already very high carrying capacity for Australia. And sure, maybe by 2099, human technology, desalination of the ocean has progressed to the point where carrying capacity of Australia might be well above 60 million. But if none of that happens, if we're just saying technology is kind of right where it is now, this might have been a pretty skeptical number, the 77.7 million. So we're going to look into this problem in a new light. It says, assume the carrying capacity is 60 million. Again, it's a controversial figure, but we had to put a number down for a math question. Use the 1960 annual growth rate of 2%. Different from the 2020 at 1.4%, it was higher. And the 1960 population size of 10 million people to predict the base growth rate and the year 2020 logistic growth rate with the logistic model. So now what example 7 is saying is, if we are assuming that the growth of humans in Australia is logistic in fact, then we need a base growth rate and we don't have it. It's first asking us to find the base growth rate. It's also saying revise the real growth rate for 2020. It's probably not 1.4%. We want to put a more accurate number on that. So again, this is a question you'll do in my lab with a different context. We're just picking on Australia for this one. But notice something that's a little bit troubling for this. Part A says, what is the base growth rate? It is not stated anywhere in example 7. We're not going to find it in example 6 at all. It's right there in the formula. So if that's the case, we need to rewrite the formula. Here's how this kind of problem would go. Take this whole formula that you see here, and you can now say, new formula. This will be a new formula you might want to come back to cite to for the MyLab question. It will be that R, which is the base growth rate we're looking for. In this formula here, we can divide this entire thing in the parentheses over the logistic growth rate and say R equals logistic growth rate divide that whole thing by 1 minus population, which is also divided by carrying capacity. Let me just fine tune these things here. Okay, so this is what we have to calculate, which means we need to find the population size, we need to find the logistic growth rate. Once we have those two missing core ingredients, we can just calculate R, the base growth rate, the fastest Australia could ever grow, according to that as a carrying capacity. Again, it's kind of a weird problem. We're reverse engineering the whole problem, recasting Australia as growing logistically. So we're going to say the 1960 population size was 10 million. That helps us out. We have a population size we can throw in. Let's put down on the left population is 10 million. So use the 1960 annual growth rate of 2% and the 1960 population size of 10 million to predict the base growth rate and the year 2020 logistic growth rate with a logistic model. Assume the 2020 population is 26 million. So what they don't say here very, very clearly, which is kind of a disservice to us, is we're assuming the logistic model holds. Any growth rate we talk about with Australia is in fact a logistic growth rate. And that's what's going on with this one. Again, I feel like this question could have probably been worded a little bit better to be more directed, kind of like some of the other questions we've complained about. Well, I've complained about a little bit on these notes. In my lab, this is about how it's written, and we have to do the detective work to say that this is the logistic growth rate. So the logistic growth rate comes out as 0.02. Once again, we have to convert that back into a decimal number, and that's what's going to go in for this value right here in the logistic growth rate. Let me just use that same color pen. So finally, we can plug those numbers in and get a value out. But any questions at the moment?
Yes, I have a question.
Yeah.
How do you know to use the 10 million as opposed to the 26 million?
Oh, gotcha. As far as the 26 million goes, we could possibly use that, but they would have to give you a percent growth rate for the 26 million figure. It would have to be assumed to be the logistic growth rate at the same time, which is why we can't even use the 1.4%. That was assuming we're using the exponential model. That's why we're using the doubling time formula. So the reason we can't use the 26 million is only because that rate was for 1960. So we have to reuse the 1960 size as well. Does that make
Okay.
sense?
Yeah, so did they just give us the 2020 population for no re like it's just additional information we really don't need at all?
Actually, we'll have to use it for the part B part of the problem.
Oh,
It won't
okay.
be growth rate for 2020, so we'll plug it in on that one.
Okay. Sorry, yeah, that was just confusing me.
No, I'm really glad you asked about that. And yeah, when I was reviewing the notes myself, it was very confusing to me as well. There's a lot of moving parts, right? There's a whole bunch of quantities. When you state a formula like this, there's really four things we're tracking simultaneously. And once they start giving you a 2020 value, a 1960 value, it feels like even more we have to be accounting for as well. So yeah, if you have any questions getting through that question, giving it another try in my lab, don't hesitate to ask about in class. I'm happy to do any problem, even from my lab, whether it's tomorrow during our review next week, I'll be happy to help out. Other questions at the moment? Okay, well, let's throw this figure in, see what we get. And when we come back on next class on Thursday, we'll finish out our part B, review just what happened here on the notes, which was quite a lot when you look at it. Take the logistic growth rate of 0.02. Using the 1960 value, we're going to go 1 minus the population size. We're writing this in millions, so this will just be 10 million divided by carrying capacity of 60 million for Australia. The millions unit, millions of people would cancel out. So it just becomes this altogether, really just a 1 minus 1/6, which is really just a 0.02 divided by 5/6. So you could work that out in stages, but no harm just dumping it into the calculator as a 0.02 divide by 1 minus 10/60ths. We get this value. We want it as a percentage. So let me write it in as stages once again, 0.024. And then finally, as a percent, just take the whole thing and go times 100, or just move the decimal place 2 spots to the right, works just as well, to get a 2.4%. So that's the base growth rate of Australia. Using all the data here, major assumption is that that's the true carrying capacity. Change that assumption and we change the growth rate. And using that now, we can finally answer a part B question because we had the missing R. But again, we're going to review this in stages because I feel like there's a lot going on in the logistic model, lots of things to keep track of. But any last questions or thoughts at all, folks, before we call it a day on this problem? Okay, thanks again for all your careful questions about this problem, this process, and these problems. Good news I want to mention is when we do Unit 8D, it's a lot nicer. The formulas aren't as bad in this particular unit. This one was kind of a weird one. So possibly I'm kind of floating the idea is that if this comes in as a final exam question, I might make that an extra credit question on the final exam because again, I feel like it's pretty extreme what we're doing here with these kind of problems on the last weeks of the course when we're all kind of tired. So it'll be a rewarding problem getting through the homework on this one and being prepared for it on the final exam. But have a great night, folks. If you have any last questions, I'll be happy to help. Otherwise, we'll be back to this on Thursday.